Start our recording. So now let me try to show you a number of examples of this concept. Okay. Now I will start with a very popular example, which is the line following robot. Okay, those of you who might have been interested in electromechanical systems from high school or from your earlier years might have tried to build one or have at least seen one. Okay, so what is the task here? The task is that there is an electromechanical robot which can essentially which goes on two wheels, and there is a free wheel that allows the robot to rotate. Okay, so that means the robot can move forward as well as rotate. Okay, so the rotation and translation is achieved by two so-called differential drive wheels. If the two wheels rotate at the same time, the robot moves forward. If one of the wheels moves faster, turns faster than the other, the robot will rotate as well as move. If basically either the wheels rotate in the reverse direction at the same speed, the robot will turn in place without translating at all. Okay, so by using these two motors and two wheels, a rich set of behaviors are possible, right? You can move forward, you can move forward while turning, you can turn in place, and so on. So what is a line following robot? You have a line on the floor, and there is an optical sensor that can see this line somehow, and the task is to be able to move forward while staying on this line. Okay, so you see that in this simple robotic application, there is the concept of a desired behavior. So you don't want the robot to do something arbitrary. You don't want the robot to just move in an arbitrary manner. You want a controlled motion. You want the robot to stay on this line and be able to stay on the line even if the line has some curves and so on. Okay, now it's interesting to see or to think about what's the input, what's the output, what's the controller, what does the controller do. For example, here the desired output is that the robot's line of motion, you can think of this as a vector. That vector is you want it to stay on the line. You don't want it to go astray to somewhere else. So what you do is you measure the output. How do you do that? Well, you place an optical sensor. As the robot moves, if the line is not in the center but deviates to the side, you sense that and you compare it to where the line is supposed to be, and you generate an error. So if you think about this diagram here, this desired signal is like where the line should be. And this line, if you think about this as some kind of a sensor, here, this is where the line is as measured from the output. And then you take the difference to see how much is the deviation, and you use that deviation. In the simplest case, you amplify this. Why? Because this is a motor, and this is simply a difference of location. So you need to somehow convert this signal as a voltage to the motor. So usually you will have something over here as well, and we usually call this the controller. It can be a simple gain, like an amplifier for the motor voltage, or it can be a PID controller, which is a much more complicated mathematical expression. Okay, but essentially what's happening is that hence you generate voltages to the motors, and those voltages will affect where the line will be. So this becomes a continuous loop, which we call a feedback system. Okay, now if this is done in a proper way, it's going to look like something I'm going to show you on the next slide. Okay, here's an example over here. I'm going to play it for you. This is from a competition of line following robots. Okay, and it's a pretty high performance competition. Okay, so what you see here is a well-designed, well-performing control system in the form of a line-following robot. You see that the desired signal is inscribed on this board and is in fact designed to be a challenge. Okay, it's designed in such a way that there are many turns, harder turns, softer turns, both ways, and the system is have a supposed desired behavior that is supposed to stay on the line while achieving the highest speed, so that you can complete this circuit in the minimum time possible. Okay, so that's a kind of a typical I would call toy example, but it's still, you know, being able to design such a system, build it, and it shows this kind of performance is actually an achievement in terms of control systems design. Now I will show you some other examples that are obviously much more complicated than that, but the basic ideas, the basic theory, the basic mathematical foundations are the same. Okay. Now I'm going to start with a funny example that I call an example from nature. I don't know whether you guys are familiar with. I am sometimes putting out videos from this channel. It's called the Smarter Every Day. This guy actually is, I don't know how many million followers he has right now, but this is one of his very early videos. You can see this video shot at home. So have a look.
Hey, it's me, Destin. I got my dad a present for Father's Day, and it's kind of weird, so I figured I'd show you an interesting principle with the present. It's a chicken. I got my dad a chicken for Father's Day, and I want to show you a pretty interesting method that chickens have to keep their head stable. You know, in guidance and control, you have feedback loops, and so you have to know your position and where your relative motion is going so you can compensate for it. But chickens are really good at this, so I'll show you. Watch his head stay totally stationary as I move his body. I can move his body in pretty much any direction, and his head stays rock solid in one position. This is really hard to do. So anyway, he knows exactly where his body is and where his body's moving. It's kind of fun to watch, isn't it? So they're really good at it. I don't really know why, but I'm sure there's an explanation. There's my sister Browley with the other chicken we got, Dad. So anyway,
tail tricks. Up, down, up, down.
look how solid his head is. That's kind of stupid. It'd probably pick me in the eyes, so I'll stop now. Alright, so bye.
The perfect Father's Day gift.
Yep, he liked it.
Okay, so you see that, you know, in actually in nature, feedback control is everywhere, and it includes us. You know, our sensors are located on our heads, you know, and these animals obviously are quite special in that respect, you know. So being able to essentially keep a desired behavior, a mechanical behavior in this case, while you acquire information from your sensors is essentially the essence of our course. Okay, so that's a very interesting example from nature, and later on I believe this video inspired I believe Mercedes-Benz to come up with an advertisement essentially promoting their latest kind of suspension system, an active controlled suspension system to show what kind of principle it's working on. Okay. Now I'm going to show you another example, and this is going to be followed with some examples from industry, then from robotics, because I'm kind of working in the field of robotics. I have very exciting examples from robotics, then from aerospace, and finally from defense. Okay, from defense industry. I don't particularly like talking about weapons in particular, but still defense electronics is essentially has many job opportunities in Ankara in particular. and it's because of the geopolitic location of Turkey. We cannot kind of escape from this. So you will see a lot of stuff is being done in the recent years in Turkey as well. Very successful stuff as well. So this one is from industry. It's about crane stabilization. So it's about industrial cranes and how they can be improved by using feedback control.
The load moves following its familiar.
By the way, it's an advertisement video. Sorry about that. So it's a kind of a bit cheesy, but concentrate on the concept.
Route, guided by an experienced operator. Everything works as it should. This is the moment which is always present when the load is moved the traditional way. The load is heavily swaying. Therefore, Kone Cranes recommends the sway control system. It speeds up load handling and makes it reliable, easy and safe. Even the most experienced operator is forced to spend time waiting for swaying and swinging to end. With the sway control system turned on, the situation changes dramatically. This is important in daily work. And of course, time is money. To top it all, it also translates into easier work and increased safety.
Okay, so that's the concept basically, and this is a very expensive system. And you know, if you look at how many cranes there are in Turkey, I haven't ever seen, you know, one of these systems used, or a crane company offering this as a let's say in-house developed technology. So it shows us that there are many opportunities for control engineers to contribute to the industry in Turkey as well. I mean, this is a well understood problem, and in fact in the fourth year you will have experiments that are almost identical to this problem. So its solution is already known, but you know, obviously a commercial product based on these principles is something else. It really is waiting for some of you guys to basically do that. Okay, so here's another example. This is a fairly old example right now, but still an impressive achievement of control systems. Essentially, control systems have been around in space travel, you know, from very early on, from 1950s, 60s, but it's fairly recent where control systems has actually penetrated to the everyday products so much. Okay, so this one is the called Segway Transporter. It's a two-wheeled device.
How is a Segway able to balance on just two wheels? The Segway is famous because it can balance itself. The reason why it can balance itself is because it has amazing motors and a bunch of computer power. In every Segway, there are two electric motors, one for each wheel. Each motor produces 2.5 horsepower. This may not sound like much given that cars can have 300 horsepower, but these motors are tiny and a Segway only weighs 70 pounds. Two controller boards provide precise computer control for each motor, and two 72-volt battery packs supply the electricity. All this technology lets the Segway perform its balancing act. 5 gyroscopes keep track of the exact orientation of the Segway. Whenever it starts to tip, the computer detects it and sends a signal to the motors so they can react. It all happens in a fraction of a second, so you don't feel a thing. It seems completely natural.
Okay, so obviously this system is a combination of almost everything that we learn in our profession, right? There is electronics, there is electromechanical energy conversion, there is very efficient motors, there are electronics drivers, there is battery technology, everything. Okay, there are computers, but essentially what makes this possible besides all that technology, is the feedback control concept. Because you have the other components everywhere, but what makes this application successful like this is basically that particular difficult mathematical solution, which we call the feedback control system, designed in the proper way. Okay. Here's a very different example from what we call a ship stabilization. This doesn't have any audio, so I'm going to try to fill in. So what's happening here is that if you have a large ship in a rough sea, the wave action essentially causes the ship to sway from side to side, from front to back. So what's being done is to add motors and pumps so that the ship basically has some water compartments that are dynamically filled from side to side, and that is compensated, or that is controlled by a control algorithm. Okay, so in that case, by using those pumps as actuators, which obviously are huge to be able to move that much water this fast from side to side, but the end result is that you get essentially a cancellation of that wavy motion that the ship experiences. Maybe on a cargo ship it might not be that much of a problem, but if you're on a passenger ship, if such a system does not exist, you usually in a rough sea, you cannot eat, you cannot sleep, you will constantly be throwing up. So these have become a very important part of modern ship technology, which is basically almost entirely our topic in this course. Okay, so that's another example. Here's another example from our early years with legged robots. Okay, this is our six-legged Rex robot. This is a line following example, similar to the wheeled robot example, but this one is different in the sense that first it's entirely camera based, so there is no optical sensor sensing the line. A camera does that, and also because of the legged motion of the robot, you get a signal that is not stationary in the field of view, but it's oscillating. So what you're trying to achieve is not a constant signal, but you are actually tracking an oscillating signal. So let me show you. So that's basically a more complicated system with a similar application. You need to be able to handle that constantly oscillating output and be able to track that in order to guide the robot into the desired trajectory. Okay, so this was a study about 2005. Let me show you some examples from the Boston Dynamics company. Now this company is special because the head of this company has been working in legged robots beginning in the 1980s. So it's a well-deserved reputation, and the company employs about 250 PhD engineers. So it's like a university over there, and that results in a very fast advancement of legged robotics, and in particular they have achieved impressive results in terms of feedback control. Now this example I'm going to open up from my hard drive because the video format is not fully compatible. So this is like a dynamic motion, a throwing motion. So a lot of control loops are happening here because not a single variable is being controlled. Okay, so you can see that there is a dynamic action. The robot is keeping its balance while achieving a certain desired behavior, and in the meantime, obviously, the arm is being controlled, the legs are being controlled, the dynamic equilibrium, the balance of the robot is being controlled. So there is a lot of complex control algorithms are active in this problem. And obviously there are many other auxiliary problems as well. So that's an example from 2013. And I'm going to show you a couple of more from this company, gradually increasing so gradually coming towards our time. So this was a four-legged robot which still was using hydraulic actuators. So you have a gasoline engine supplying power and hydraulic fluid to the legs. So there is again a lot of control being done at different levels at this point. But the main task here is locomotion. So you are trying to move this huge robot on its legs dynamically, running, jumping, turning, and there is a lot of interesting problems around this platform. And I'm going to show you how this platform actually diminished in size to become gradually something that is commercially viable. Initially, this company was shooting for defense contracts, for the military. So legged motion, legged robots obviously are a very, I would say, complex application area for control algorithms. There are many interesting theoretical and practical problems. Obviously some companies are pushing ahead, but for example, Mert Hoca is interested in this area. I am interested in this area. So this is an area which with a lot of very exciting developments. This is a bipedal robot, again from about the same years, again from the Boston Dynamics company. What is special about these platforms is that there is a dynamic balance here. So if you stop the robot, like in human beings, right? If you sleep on your feet, you will just fall down. So the reason you are upright is because your brain is constantly applying a feedback control loop. The sensor is in your inner ear, gyroscopes, and your eyes are seeing surrounding you, so that your brain, in fact the lower levels of your brain are constantly closing this loop in order to keep you upright, allows you to run, to walk, because your feet are so small that if you stop these algorithms, you cannot actually stay on your feet. Okay, so those algorithms are constantly in operation. Okay, so this is from 2017. It's kind of getting scary at this point, but this is where essentially this technology is maturing to. Okay. Now at this point, you can see that there are no longer gasoline engines involved. So it's all evolved into electrical motors. As the electric motors have become more and more powerful, more and more capable, and that is combined with battery technologies, many advances in our profession, and it's combined with control algorithms in order to achieve a self-sufficient, you will see some more examples which are also power autonomous, where you don't have any cables, you don't have any extra power, but everything is self-contained in a single unit. This is a robot called Spot Mini, where it's becoming kind of a commercial product that you can, at this point, you can purchase. Still very expensive, but at this point, universities are starting to buy platforms like this. So there are many control algorithms here, right? Control of the locomotion, control of the task, control of the collaboration, control of the manipulator mounted on top of the robot, and so on. Okay. Now I'm going to switch to another example, which is from space. Okay. SpaceX company has, in the recent years, have achieved incredible advances. Obviously, space and space exploration was the driving force behind early control algorithms as well, like 1960s. A lot of discoveries made, but there was kind of everything was saturated for a while. But as you know, if you're following this area, SpaceX was able to construct reusable rockets that can land back to Earth instead of just falling to the ocean. So this is their first achievement. This is a Falcon 9 rocket. So what's happening is that you launch the rocket goes into space. The lower propeller, the lower part, the thruster part, is separating from the upper part, which goes into space. And that large section actually still has fuel in it, and it just falls back to the Earth for a while. And then it opens up control surfaces like these wings that I'm going to show you in a minute. Then using these, as well as the rocket engine at the final stage, it actively controls itself in order to land on its feet on the ground. Okay.
Stage 1 entry burn has started.
So at this stage of the video, the rocket is falling back to the Earth. These wings are opened. So you will see these moving. They are being moved by a control algorithm or multiple algorithms, essentially, feedback algorithms. The right-hand side is the section in the space. So you concentrate on the left. So this is falling back. You see some jets being activated, as well as these wings being used in order to direct the rocket to its landing location.
Coming up now on the first stage landing. Second stage continues to burn nominally.
Stage 1 is transonic.
So it's initially a controlled fall, and then it activates its rocket engine and then actively lands itself.
There are the twin sonic booms.
Landing legs not deployed. Stage 1 touchdown confirmed. Landing operators moving 11.100 on recovery net.
Stage 1 shut down.
If you're interested, there are many other videos showing different versions of this rocket. I'm going to show you one more video which actually shows the development of this system. So it shows you how different stages of development basically had different levels of success and different heights and so on. Okay. So this is a multi-year development. So this one is interesting because you see one of the rockets usually there may be multiple stages. They land at different locations. One of the stages usually land in a again automatically controlled raft that is in the ocean. Both the raft is being navigated automatically to the landing area, as well as the rockets having a controlled descent to come back to land. So it's again, you know, I find it very impressive achievement in terms of control systems in the recent years. Okay. Now there is also you might know in new kind of system that is called the Starship. Starship is much bigger and is supposed to replace the shuttle, the space shuttle program. They have been trying to have high altitude tests for the Starship. This one shows a failure. This failure was followed by a successful landing, by the way. But the failures obviously show how you have to be kind of vigilant, and you need to work on improving the system. Even these systems with huge budgets actually can have disastrous, failures, but that's part of building a successful system. So this one is the failure of the Starship test vehicle. It shows how the control system fails because of a malfunctioning actuator.
30 seconds, all three reactor engines at power. Starship climbing to 10-kilometer altitude.
By the way, this system is so-called vector thrusting. Vector thrusting means the motor assembly actually moves in order to direct the rocket thrust in a certain angle. So the control system adjusts the angle. By changing the angle of the thrust, rocket thrust, you can actually make the rocket move in different directions.
On the right shows three reactor engines burning. 4.5 minutes, we are handing off to the LOX tank. We are beginning to flip to horizontal. And the white cloud, the plume you were seeing was intentional. There's a liquid oxygen dump. We've now transitioned to horizontal and beginning the subsonic test portion of the flight, where we check out the aft and the forward flaps to hold the vehicle stability as we descend back to the landing pad. We're preparing to restart 2 engines, flip the vehicle vertical, then transition to 1 engine for the landing burn. As you can see from the scene, we had again another great flight up to the 10-kilometer apogee. We demonstrated the ability to transition the engines to the landing propellant tanks. The subsonic reentry looked very good and stable like we saw again last December, so we've got a lot of good data on flap control. And again, we've just got to work on that landing a little bit, but we'll find out
Okay, so kind of a major loss, but obviously this is like a gradual improvement, and in fact the next test that you can find on the internet was a successful test actually. Okay, so I will finish off by 2 more examples. These are from our own defense industry, collaborations between Aselsan and Roketsan. These are defensive rocket technologies that are being developed. One is an anti-ship missile called Atmaca. So, I mean, obviously space programs excite us, but at the same time, we sometimes think about, okay, what's going on in Turkey? Rest assured that there is a lot of stuff also going on Turkey. And also most of you, some of you will be essentially international people working in different industries across the world. But these are 2 examples of what's happening in the defense industry in Turkey.
Turkey's Atmaca anti-ship missile was successfully test-fired twice from an Ada-class corvette this week, marking a major milestone for the program as it achieved initial operational capability. Both launches took place from Turkish Navy Ada-class corvette TCG Knalada, the last shipping class. According to our information, the first test took place on February 3rd and consisted in a telemetry test without the warhead. The next day, an Atmaca with a live warhead was tested. Both tests were successful, meaning the missile has now reached IOC with the Turkish Navy. For the record, the first at-sea test of Atmaca took place in November 2019 from the same corvette. TCG Knalada is currently the only Ada-class corvette equipped with Atmaca launchers, and therefore this corvette was used for the development of the missile. Atmaca was unveiled for the first time by Turkish missile systems company Roketsan during IDEF 2019. According to Roketsan, Atmaca is a subsonic sea-skimming anti-ship missile with a range of over high resistance to countermeasures and all-weather capability. Atmaca is said to become the anti-surface warfare weapon of choice aboard Turkish Navy modern surface combatants. It will be fitted aboard the Ada-class corvettes, the future Istanbul-class frigates, and the future TF-2000 class anti-air warfare destroyers.
So this system is both has a rocket engine as well as a basically I would say a turbofan engine. So it just launches with the rocket engine, is being controlled for a while, and then it just gets rid of the rocket engine and it switches to its jet engine, and it flies over the surface of the water for 250 kilometers autonomously, and then basically arrives at its destination. There is another. There are many such projects, but another one which is interesting is the Hisar-O missile. It's a high altitude air defense rocket basically, so it's different from this C version. So I'm gonna just, so this one is like kind of a promotional video. So obviously these systems are the cutting edge of control engineering. But as you have seen, it's not only about the defense industry. There are many civilian applications as well. And I believe Turkey will also be involved in space technologies as well. So, many opportunities there. Okay, so in any case, I've kind of tried to avoid the theory, because we will spend almost the entire rest of the term trying to see how these are possible, what kind of mathematical background makes this kind of achievements possible, and hopefully you will get a very good idea about how these systems work. And some of you will be, I hope, involved in your professional careers, as well as in later years in your graduate studies, in your fourth year studies, graduate studies as well in the field of control systems. Basically, these are exciting kind of mathematical tools that result in non-trivial achievements. Okay, these are not possible by just thinking about them. Okay, you have to learn what kind of underlying technologies and what kind of underlying mathematics are involved. Now I'm leaving this what's in the box question for a while. I guess I'm going to put down a short video in Metu class revealing what's in the box. But in the meantime, please use that, I'm going to maybe extend the time of that survey. Please bring in your suggestions, and you will see what's in there. It's a funny item in the box. Now let me conclude by again reiterating our goal. Okay, so what we are aiming, our goal is through simple and more complex mathematical models and tools, we will try to understand how systems behave in terms of stability, transient behavior, steady state behavior, and we will also aim to learn how to use feedback to make them behave in a designed way. Okay, we will also use computer tools in order to implement these theoretical concepts, to make them work, both to implement control systems, and we will also use numerical simulations in order to solve the mathematical models in order to understand the behavior of such systems. I mean, as an example, if you think about the PSpice program, I mean, for an electrical circuit, you use these simulation tools in order to solve the underlying differential equations of an electrical circuit in order to know about the voltages and currents in an electrical circuit. So we will again use similar simulation tools, in particular MATLAB and Simulink, in order to analyze those mathematical models of systems in order to show the behavior of variables of interest, often physical variables like speed, position, velocity, things like that, with respect to time. Okay? So, usually I kind of transition from here to the board to continue with, essentially the basic parts of a control system and the feedback concept and how we can derive the transfer function of a feedback system and so on. But I guess we will continue these next week. Most likely Mert Hoca will be taking over and hopefully taking you guys slowly to the mathematical modeling, and then we will move on from there following our plan. Okay, so thank you guys for staying tuned. I see that 177 people remains, so just a bit drop from 220, I believe. So see you guys next week. Eğer sorusu olan varsa, kalmak isteyen varsa ben bir miktar daha kalabilirim. If you want to stay and ask questions, we can stay for a while. Otherwise, you can sign off.